All right. So in the last class, we did the tabular method, or the other name of it was Quinn-Mikulski method. So the advantage of this particular method was you can go or you can simplify the Boolean expressions if your Boolean variables are greater than 5 variables. Okay, so that was the method. Though this is a lengthier method, but for any variables, even up to a variable of 10, you can do it systematically. You will be able to simplify it. Whereas with K-maps, the visualization of variables beyond 5 is really difficult. Now let's still do some more examples using K-map. So more examples here. So you have to implement this particular function, not more than 2 NOR gates, right? So what does this particular function means is this f is a 4 variable function here, which is 2, 4, 6, 10, and 12. D represents that this is a don't care function. This is a don't care function. So don't care function in the sense across these particular cells 0, 8, 9, and 13, you will put a X mark. So let us see here. So a K map has been drawn. So it is 2, 4, 6, 10, 12 will have ones. So it is 2, 6, 4, 12, and 10, right? So they are all having ones, and 0, 8, 9, 13, they are having x's. So they are having x here, x0, and then 13, x, 8, 9, x, 0, 8, 9, 13 x's. So now what is asked here is you have to implement using NOR gate, right? So two NOR gates. We all know that NAND gate is used for SOP implementations, right? It'll be easier if you do an SOP implementation using NAND gate. And again, if you want to implement a POS implementation, then NOR gate are the best one. Though the given function here is an SOP function, but you are asked to implement using a NOR gate. So logically, it makes sense to implement using a POS function here. So instead of combining ones, it is good to combine zeros here. So again, how do you use the don't cares? We will use our don't cares only if it is advantageous to us. If it is not advantageous to us, we will not use it. So here you can have a larger map here, the one that is drawn in the orange map, and one more zero that is left here is a zero is left here. Now, what will be the POS expression for this? Don't follow this particular part. Here, first, this has been written as a complement form, and then it has been uncomplimented. So that is the reason. So I've already taught you. So if it is all the rows, then A and B will automatically vanish. For the columns, for 0, 1 column and 1, 1 column, the only variable that will be left will be D bar. Since we are writing for POS, I am writing D bar. And then for this 0, 0 combinations, this corresponds to 1, 1. So in POS, it will be A bar, B bar, A bar plus B bar. Am I right? A bar plus B bar. And since this is POS, this will be a dot expression. A bar, B bar. And then along the column wise, this will be plus C bar. Am I right? So this will be your POS expression. Okay. Now what is done here is for the zeros, the SOP expression has been written, that is D plus ABC, and then it has been complemented. So De Morgan's law has been applied here. So when you apply here, it will be D bar dot A bar plus B bar plus C bar. Both are same. Either you write directly in a POS form or you write in an SOP and then take the complemented form. Okay. Now coming back to the NOR implementation. Again, this expression itself shows that this can be implemented using a NOR only. And the thing that they have asked is only two NORs, right? Only two NORs in the sense your objective first is to whenever you're having a dot, then AND gate or NAND gate will be possible. So you will have to first remove it. How do you remove it? Apply De Morgan's theorem here. So put double bar here and then remove that particular dot here. So when you remove that particular dot, this will look like D plus, because one more bar will be coming here when you split this. So bar and bar will go. So only D will remain. So D plus A bar plus B bar plus C bar whole bar. So this can be implemented simply like a 3-input NOR gate with inputs as A bar, B bar, C bar, and another input as D. So you are implementing using just 2 NOR gates. So this is how you do this problem. Now, now uh, we have seen multiple times, especially in error detecting codes or error generating codes, that is something similar to Hamming codes, right? Every time you wanted to generate a parity bit. So how do you implement that particular parity bit? Say, for example, what do you mean by a parity bit is, say, you are having a 3-bit input, right? So if it is 0, 1, 0, if I want to send this particular bit over a sequence and I have to have a even parity checker and even parity generator to make this combination and even parity, one has to be generated here. Am I right? So I have to create a 1. So this particular bit position is generated by a parity generator. Right? This is generated by a parity generator. Why we are using this parity generator? Because we want to send even number of ones along our transmission channel. Now, and there is another kind of a circuit which checks the parity at the receiver end. Say, for example, you are sending this particular bit 1010 and it is getting received here, right? I am receiving this particular bit now. When I receive this, I cannot manually check every time whether I'm having even number of ones or not. So I have to design a digital circuit that will check whether I'm having even number of parity or not. How these kind of parity generators and parity checkers are implementable is using XOR gates. So how you can implement using XOR gate is, we know the truth table of an XOR gate. What is the truth table of an XOR gate? If I have two variables, say A and B, my output is Z, or for your convenience, let me change the variables to X and Y here. If I have the three variables X, Y, and Z are the P is the output variable. Let me keep. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. So whenever I'm having even unequal number of ones, I will have ones, rest I will have zeros. Okay, so if I use a parity generator, say for example, this is a 3-bit parity generator. So this output P here will be fed to this particular point. Let us assume that my X value here, Y value here, and Z value here are my 3 inputs. This can be easily implementable using XOR gates. We know that when I have odd number of ones, my output will be equal to 1. So this obviously checks X XOR Y XOR Z. My output will be 1. So my parity generator bit output will be 1. In case if I have this as 0, I'm so what is X XOR Y? It is 0 XOR 0 is 0. And again, that output XOR 0 is still 0. So my parity generator will generate 0 here. And this is something like it is checking the even number of ones here. So hence, the XOR gates are normally used for a parity generator circuit, normally for an even parity generator circuit. Now, what will you do if you want to generate an odd parity generator? Anybody? Quickly, can you answer? I want to generate an odd parity generator circuit. What will you do? Just one simple change you need to do. Anybody? Quickly, please. We don't have time. We are already very slow in our lecture. I want to generate an odd parity generator. Complement it exactly. So exactly, excellent. So the only thing that you will do here is, if you want to have an odd parity generator, either put a bubble here, or bubble means what? You put a NOT gate here. right? So if it is 0, it will get 1 is generated. If it is 1, then 0 will be generated, which is nothing but your odd parity generator. Good. Now, what about even parity checker? Even parity checker, that is, I have to check. Previously, generator was using these 3 bits to generate this parity bit. Now, if I want to check, I will check all the parity bits. Simple. Again, what you do is XOR all the uh, bit positions, including the P. So which means X XOR Y XOR Z, and you XOR the parity bit also. Okay. So when you XOR the parity bit, it will check whether it has got even number of ones or not. Obviously, you know that XOR is an odd functions. XOR gate function is an odd function, which means that it will it will give you an output of 1 if you have odd number of ones. If you have even number of ones, it will give you an output of 0. So which means that if I have like this, I'm having odd number of ones, then it will say, it will alert, it will give you an output of 1 here, telling that there is an error output. Error output in the sense the bit that has been received has got even odd number of ones instead of even number of ones. If say for example, I have a parity bit 0 here. Already there is an even parity here. So it will generate an output of 0, telling that there is no alert and the received bit sequences have no error. So this is how you generate a even parity checker, right? C, yeah. So C will be equal to 1 if error occurs. That is if 4 bits received have odd number of ones. The same bits can be used as generator also if your P bit is equal to 1. So the same circuit you can use it otherwise. So for odd parities, what you will do is you just XOR, or the other form is, you can put, yeah, either put bubbles ahead of the gates or even after the gates also. So we know that X XOR 0 is X and X XOR X is 0. This is the basis of even parity generator, and this is the basis of odd parity generators. Okay, all right. Okay, now we are having the just a representation again of the functions of XOR. Let us assume that you have 3 inputs, and the output of an XOR gate of a 3 input is when you have odd number of ones. When you have odd number of ones, you will have output as 1. You can see here 0 1 1, even number of ones, your output is 0, right? And even number of ones, your outputs are 0. Odd number of ones, your output is 1. Hence, if you write the SOP function of for this particular Y, which is nothing but A XOR B XOR C, if these ones can be written as A bar B bar C, A bar B C bar, and for this one it is A B bar C bar, and for the last it is A B C. This has been written as an SOP function. In terms of min terms, it is 1, 2, 4, and 7. And you can clearly see here that this is an odd function telling that odd number of ones you get an output of 1. If you want an even function, then simple, you will have to complement it. Complement in the sense you just take the y bar of it, right? You take y bar of it. If this is an odd function, and if you are taking a complement of this, this becomes an even function. So what will be the complement of this? This will become 1 0 0 1 0 1 1 0. So you can see that you have, whenever you have even number of ones, your output will be 1. Okay. Now let's do some more K-maps and then let's move on to combinational circuits. So how do you simplify this? Though you might have got experience, and let's do here. Um, okay. So the first variable here, this is a 4 variable map. It is already given here as a 4 variable map. So what you should do here is first take min term by min term. A, B bar, C, right? So it is A, B bar, C. and D variable is missing. So A, B bar, C corresponds to what? 1, 0, 1, and then a hyphen. What are the two possible combinations for the leftover places? 1, 0, 1, 0 is one possible combination. 1, 0, 1, 1 is another possible combination. Likewise, you do it for all the variables. So here again, this corresponds to B bar, C bar, D bar corresponds to what? That is A is missing here. So it can take either 0 or it can what, take 1. And then B, C bar, D bar corresponds to 0, 0, 0 and 0, 0, 0. Okay. And similarly, BCD corresponds to 1, 1, 1. So either it is 0, 1, 1, 1 or 1, 1, 1, 1. Similarly, ACD bar corresponds to A hyphen C 0. Either it can take 1, 0, 1, 0 or 1, 1, 1, 0. Similarly, the A bar, B bar, C corresponds to 0, 0, 1, 0 and 0, 0, 1, 1. And the last one corresponds to 0, 1, 0, 1. Now let us write this corresponds to what? 0. This corresponds to 8. This corresponds to 7, 15, 10. This corresponds to 14, 2, 3, 5. This is 10 and this one is 11. Right? So I hope I have made it. So we have got 0 here. 1 is not there. 2 and 3 are there. 2, 3. And then what we have is 5 is here. So 0, 1, 2, 3. 5 is here. 6 is not there. 7 is there. 8 is there. 9 is not there. 10, 11 is there. And then 14 and 15. 14 and 15. All right. So this is how we have made these ones. And it is now fairly simple to combine. Your objective is to create 4 variable map. So what are the 4 variable maps that are possible? It would be easy if I could draw it here. Or should I skip this because we are running short of time? Okay, I hope you can do it. So these ones can be combined using a 4 variable map like this. These ones can be using a 4 variable map. All the corners can be combined. And then this combination can be done with a 4 variable map. So only a 2 variable map that will be left will be only this will be the only 2 variable map. Now, so this is the SOP simplified expression for the given set of min-term expressions. Now, similarly, you can do it for the rest of the example also. So for a min-term function 4, 5, 7, 12, 13, 14 is given. So 4, 5, 7, 6 is not there. So 4, 5, 7, 12, 13 and 14. Rest all these three are don't care. So you can have a 4 variable map here, 4 variable map here, and then a 4 variable map, 3 4 variable map. So okay, so and then you can find out the simplified expression for this. So you might have got now a kind of an experience in solving these circuits. Let's move on to combinational circuits. You have done some combinational circuits already in your laboratories, but however, theoretically we will start now. So whatever things that you have done so far, your objective was always to simplify it. There are 2 digital processing techniques that you have studied so far. One was the Karnaugh map, other was Boolean algebra. And in fact, in addition to this, there was one more term which is called as the Quine-Mikulski method also. This also you studied till your mid-semester examinations. So now this is not enough, right? So what must be our objective is we have to design the digital circuits. We know how to simplify a digital circuit. We know how to implement a digital circuit, but you have to design a digital circuit. So whenever you wanted to design a digital circuit, what do you mean by a design? Whenever we say a design, there will be first a problem statement. Say for example, you will be given a problem statement that count how many people are entering a classroom. So you have to, this is the problem statement. So you have to design a digital circuit for that. So how is it possible? So first thing is, with the problem statement, first you have to decide what kind of digital circuit are you going to design. Whether you are going to store a data or you are not going to store a data, all those things are essential. Based on that, your digital circuit designing has been classified into two types. One is called as a sequential circuit and other is called as a combinational circuit. Now, what is a combinational circuit is whatever you have studied so far, they are some kind of a combinational circuits only. Now, what do you mean by combinational circuits? Let me explain. Any combinational circuit will have a digital circuit, in fact, with n number of inputs and n number of outputs. And these n inputs and n outputs depends on how many input variables you are going to have. What do you mean by that is, it means that uh, and okay, we will come back to that particular point now. If you have n number of inputs, if you are giving some inputs here, okay, there will be some kind of a processing that will be done in the block. And this block is nothing but a combinational circuit. This combinational circuit is nothing, it consists of nothing but the digital logic circuits only. It all consists of just digital logic circuits. And it will immediately process, and with a gate delay, you will get your output. What do you mean by gate delay is, say for example, you are having uh, one gate, a gate something like this, some gates like this. The gate delay means, what does it mean is, you are giving an input. The input is processed in gate number 1. It is passed on to gate number 2. And then the time taken by the gate to process your input is called as the gate delay, right? So if you are giving your input at say time t, then you will get an output at time t plus say small delta t times. If you are giving time at say 1 nanosecond, you will get your output at say for example 1.1 nanosecond. So which means that zero point 0.1 nanoseconds will be the processing time of these gates. Okay, so that is how the combinational circuits are. So what do you mean by a combinational circuit in short is, a combinational circuit is a circuit that will have n number of inputs, n number of outputs, and a logic gate. We call them as a combinational circuit. Now, the point here is, how do you decide that you will have so many number of inputs and so many number of outputs? The number of inputs that you have here are decided by the number of input variables. What do I mean by input variables? Say for example, we want to process a 2-bit function. We want to add 2 bits. Then what are the 2 bits possible? A and B are the 2 bits possible, which means that the input variables are A and B. If there are 2 input variables, how many input combinations are possible? So there are 4 input combinations are possible here. So your input variables corresponds to the total number of inputs, and at the same time how many possible inputs are available. You will have 2 power n possible combinations are available. So with n input variables, there are 2 power n possible combinations of binary input variables are possible. Similarly, the output depends on what kind of logic that you want. Now coming, so this is what is a combinational circuit is. Now the next kind, the other kind is called as a sequential circuit. What do you mean by a sequential circuit is, the difference between a combinational and a sequential circuit is, sequential circuit will have some kind of a memory element. As I said in the previous example, you want to count how many number of students are entering a classroom. Okay. Now, if the digital circuit that you have designed just displays the count number, then it is a combinational circuit. If say for example, you come the next day and you want to compare the number of students entered the classroom with the previous day, then the previous day's data must be stored in a memory. Then those kind of circuit will be called as a sequential circuit. So in short, a sequential circuit is nothing but a combinational circuit, but it will have a memory element to it. Normally, in digital circuit, the memory element, there is another name of a memory element. What is the other name of a memory element is a memory element called as flip-flop, right? So in short, it is written as flip-flop. We will study in detail about flip-flop. There are four different types of flip-flops you have. So the memory element that we consider here is a flip-flop. If you have a flip-flop and if it is storing some of your data, then it means that it is a sequential circuit. The name itself will tell you a sequential, right? So it is storing something and it is doing in a sequential manner. The sequential circuit is also further can be classified into two different types. That is asynchronous type, asynchronous sequential circuits, and synchronous sequential circuits. What do you mean by asynchronous and synchronous sequential circuit is if it is a synchronous sequential circuit, all the digital circuit that you have here inside this combinational circuit and the memory element, everything will go in synchronous, meaning everything will be controlled by a common clock. There will be a common clock input also here, which will control all the inputs simultaneously in a synchronized manner. Whereas in case of an asynchronous sequential circuit, your clocks will not be synchronized. So that is the difference here. Okay. So now what is the design procedure for we will come back to the sequential circuits much later. After we complete this combinational circuit, we will come back to the sequential circuit, and sequential circuits are the more important type of circuits when compared to combination. Now, how do you design a combinational circuit? First is, as I said, problem statement will be given. Find out uh, how many cars are parked in the parking slot. This is a problem statement, right? So in order to find that immediately as design engineers, you must first find out how many input variables are available, how many output variables are available, right? So you have to identify the input variables and output variables. Once you identify the input variables and output variables, you have to then create a truth table for it, and you have to relate your input and output. We will do multiple examples today. We will relate your input and output by creating a truth table. Now, so which means that it will look something like this. It will look, you are going to have a truth table here. You are going to have a truth table with input on the side and output on the side. Output may be multiple variables here. And after you create the relationship between input and output variables, you will create a Boolean expression here, either using K-map or even using algebraic manipulations. So each column across the output will have an algebraic expression or a Boolean expression. Okay, and once you create a Boolean expression, you will draw the logic diagram, and that logic diagram will be your combinational circuit. We will design one. So and either there are two design methodologies again in a combinational circuit. Either you have a gate level design or a block level design. Mostly design engineers, if you are using some kind of a software, then you will normally prefer a block diagram method. Since we are designing from the scratch, we will be doing gate level method. So gate level method means with logic gates. Okay, so what is your objective? What must be your objective is always whenever you are designing any digital circuit, you must keep in mind that the cost of your digital circuit is very less. Very less in the sense there should not be any other circuit with a low cost circuit than you have designed. What do you mean by a low cost circuit? Which means that the number of gates that it uses must be less. The number of ICs that it uses must be less. Which means that, say for example, I'm having a digital circuit with, say, for example, 5 gates. Let us assume that I'm having 5 OR gates, which means that somebody else have designed a circuit. Let me assume 4 gates. Okay. Somebody else have designed with 3 gates, right? Which one do you say that uh, which circuit is a less costlier circuit, whether it is a 4 gate circuit or a 3 gate circuit? Let me see some responses. Any response? Which gate circuit is less costlier, whether it is a 4 gate circuit or a 3 gate circuit is less costlier? Response please, quicker. 3 gate circuit is one answer that I have got. Anybody else? Okay, 3 gate. Okay. Now I have a point here. If for a 3 gate, if you look at an IC here, right? All these gates are available in IC. You could recall that inside an IC, you have 4 different gates, right? So if I'm using an IC, whether I use a 3 gates or if I use a 4 gates, I'm going to incorporate the same cost only, right? So in this particular case, I cannot really say that I have saved a cost because I'm using one IC only. Only difference between the implementation of these two circuits is I have used only 3 gates of this particular IC here, but I have not used one of the gates in it, but I have used IC. The IC cost is the same. If this IC is costing around 80 rupees, I have to anyway spend 80 rupees only, whether it is 4 gate or a 5 gate IC, whether I'm using a 3 gates or a 4 gate. If I have compared it with a 5 gate, if I've compared it with a 5 gate, then I have to get 2 ICs here. Why? Because 4 gate is implementable with one IC, and for now for you to implement an additional 1 gate, I have to spend one more 80 rupees to get this IC again because I need one more gate from this IC. So, but when you compare this 4 gates or 3 gates, which is advantageous, definitely, as you all mentioned, 3 gate is more advantageous. Why? Because again, the power dissipation or the power consumption with 3 gates is lesser when compared to the power dissipation in 4 gates. Okay, good. So now when coming to discussion about this ICs, people classified these ICs based on the number of gates that you have inside the IC. If you are having, say, 12 gates, then they call it as a small scale integration circuits. If you are having until 100 gates, 12 to 100, medium scale integration circuits, 100 to 1000, not 1000, 10,000 gates, there's large scale integration circuits, and very large scale integration circuits till a lakh, 10,000 to 1 lakh gates. We call them as very large scale integration circuits, and ultra large scale more than 1 lakh gates. Okay, these are some of the classifications. Again, always please remember that we have spent a lot of time discussing on why it is important for you to have lesser number of gates and lesser number of ICs, because your objective must be to reduce the cost, right? And as an engineer, this must be your aim. Always you will be liked by a company if you are able to save some cost for the company, right? So that is why a lot of IT solutions are coming up, so that you save a lot of money. So when we say reducing the cost in case of a circuit design, what does it mean is it means that we have to reduce the number of gates. Where reducing the number of gates means what? Reducing the number of ICs. So this has a multiple effect. When you have lesser number of gates, obviously you have an increased speed also, right? Because the gate delay will not be there for a lesser number of gates. And at the same time, there will be a design simplicity also, right? And the IC, the gates that you are using must be reusable, right? So the reusability property. Oh, 1 minute, I got a call. Sir, I'm in between my class, so I'll join after my class. Okay. All right. So sorry. Okay. So this must be your objective. Now let us take one example. We have 10 more minutes. Um, let's take a gate level design. One example. You have studied about half adder. What is a half adder? Let us half adder means I have two inputs, say A and B. My two outputs will be there, sum and carry. And if I create a truth table, so what is the first design problem? My design problem is design a half adder, right? So design a half adder. So this is my problem statement. Once I create a problem statement, I identify my input and output variables. So for a half adder, what are my inputs and what are my outputs? Obviously, you know that half adder adds 2-bit inputs. So I've got 2-bit inputs here. I've got 2-bit inputs here and 2-bit outputs here. Okay. Now, what will be my, so that is the second step. I have identified what are my input variables and what are my output variables. I have identified that my input variables are A and B, and I have identified my output variables are sum and carry. Now, what are my uh, input possible combinations? My input possible combinations are I can have A and B as 0, 0, 0, 1, 1, 0, and 1 and 1. These are the possible input combinations. So now I have to create a relationship with my output variables. So what is 0 plus 0? 0 plus 0 is 0, right? So I have my sum as 0 and I don't have a carry. So my carry will be 0. What is 0 plus 1? It will be 1. My carry will be 0 here. So my sum is 1, my carry is 0. What if 1 plus 0? It is 1 here and carry is 0. So 1 and 0. What is 1 plus 1? 1 plus 1 is 0 and then I will get a carry here. So my carry will be 1. So 0 and 1. So my third step is also done. I have created a relationship between my input and output variables. I have created a relationship between my input and output variables. What will be my fourth step? Fourth step will be to create a Boolean expression for each column of my output variables. So I have to create a Boolean expression for this column and I have to create a Boolean expression for this column. Now, how do I create a Boolean expression for this column? What will be my, so for sum, the expression will be, I'm having ones here. So I have to write the Boolean expression for sum, which corresponds to this one corresponds to A bar B, and the second one corresponds to A B bar. What is the comment? Okay, A B bar. And what is this particular circuit? A bar B plus A B bar you have come across somewhere, right? This is nothing but the XOR gate. So A XOR B will give you the sum output. Now carry corresponds to, this is the output of a carry here, and this corresponds to this input A B. So carry corresponds to A dot B. So how can I implement this circuit here? I can implement this circuit using, so I have two variables A and B. I have two variables A and B, and then I have an XOR gate. So this will be my sum output, and I will have A and B output and an AND gate. This will be my carry output. All right, I have my carry output. So now this particular block here corresponds to the combinational circuit. This block here corresponds to the combinational circuit, right? This is nothing but the combinational circuit. This is how you design any combinational circuit. And this is a gate level combinational circuit. You see here that A and B are the two inputs and sum and carry are the two outputs. Yeah. So this is how you got sum here, sum as x dot y, and sorry, sum as x or y, and carry as x dot y. We have already done this. So henceforth, from next time onwards, we can just, you need not every time draw the XOR gates here. Instead, simply what you can do is, if you want to represent a half adder, just create a box and just write that half adder. You know that you have got an XOR gate inside and sum and carry. So this is a gate level design. This is a gate level design, and this is a block. You have converted it to a block. This is a block level design. Still, this is not exactly a block level design. I will explain in the, when we design the full adder, I will explain what is really the block level design is. Any doubt? Okay. There was a comment, I believe. Okay. XOR. All right. Okay. Great. So now let's quickly move on to full adder. What is full adder and half adder? Half full adder means, it is not really the exact meaning of full and half. So if half adder is 2-bit, it is not 4 bits for a full adder. Uh, Full adder is again a combinational circuit, but it will perform an arithmetic sum of 3 input bits. Why do you want to have a 3 input bits? Because whenever you are adding, every time you will have a carry here. Let us take an example here. Okay. What is the problem statement here? You have to design a full adder as the problem statement number 1. Second step is, you have to identify what are its input variables and what are its output variables. How many input variables are here? There will be 3 input variables. And what are the output variables? There will be 2 output variables will be the design. Now second, you have to create a relationship between them. Now let us take a simple example. Then let me tell you what is the need for you having a um, full adder. Let's take an augment and an addend. Here augment here is 1011 and addend is 1110. When I add this, see, I'm having 1 and 0 here. When I add this, 1 plus 0 is 1. So there is no carry here, right? So 1 plus 1, so which means that here literally I'm adding 3 bits here. I'm adding a 0 also, I'm adding a 1 also, and I'm adding a 1 also. 1 plus 1 is 0, and I will get a carry here. So, and again I'm adding 3 bits here, 1 plus 0 plus 1 plus 0, 0, and I'm getting a carry here. So again I'm adding 3 bits, so the resultant is 1, 1. And you look at what is your augment and addend bit size. It is a 4-bit augment and 4-bit addend, but your sum is a 5-bit sum. So which means that you are getting, so this will be your sum part, and this will be your what? Carry part, right? So this will be your sum part, this will be your sum part, and this will be your carry part. At the same time, you are taking into account of, by taking into account a 3-bit addition, you are also taking into account a carry bit also, right? So this is not an another. So what are the variables I can have? If I assume that my augment is, say for example, some variable as say x, and my addend is y. What is my third variable? My third variable is this is a carry bits, right? So this is a input carry bits, because these carries are input carries that is going to add with your existing 2 variables. And what are your output variables? My output variable is going to be sum, and my output variable is going to be carry. Okay, so this is how we need. So which means that we need 3 bits here. So the addend, the augment, the carry in from the right side. At the same time, so which means that your full adder will have 3 inputs, and we know that you can implement this full adder using half adders also, which is what is called as a block level design. Now let us design, 2-3 minutes are there. Let us design the full adder first. So quickly let me design. So what are my input variables? My input variables are x, y, and carry in are the 3 input variables. These are my input variables, and these are my output variables, my sum and carry. If I add a 0 plus 0 plus 0, it will be 0, 0. 0 plus 0 plus 1, it is 0, 1. Maybe I will use the calculator for you, right? So don't think that why I am using a calculator here. there is a meaning when I do the subtraction, you will understand. So what is 0 plus 0 plus 1? It is 1, right? So your sum is 1, your sum is 1, and carry is 0. So likewise, you can fill it up. Uh, I will use, I have purposefully used this calculator because I wanted to show you something. What is 0 plus 1 plus 1, right? Oh, this has to be a binary addition, right? So I should not do this. Yeah, okay. Look at this particular part. 0, 1, 0. Right? 0, 1, 0. So hence it is 1, 0. Similarly, if I add 1 plus 1 plus 1, look at the binary value. Oh, sorry. 1 plus 1 plus 1. Look at the binary value, binary part here. It is 0, 1, 1. So it is 1 and 1, right? Okay. Now, having got the truth table, we have to create the Boolean expression. So what is the min term for sum term and carry term? My sum term is 1 at 1, 2, 4, and 7. So 1, 2, 4, 7 corresponds to my sum. Remember this because we will be using this later. 1, 2, 4, 7 is sum. And similarly here 3, 5, 6, 7 is carry. So you create a truth table for this. So this is what is the truth table. So 0, 1, 2, 4, and 7 corresponds to the sum part. 1, 2, 4, 7 corresponds to the sum part, and the carry part corresponds to 3, 3, 5, 7, 6. Okay. So now we have to simplify this. Um, 1 corresponds to what? X, Y bar, Z bar, and this one corresponds to, no, this corresponds to 0, 1, 0, right? So which means it is X bar, Y, Z bar. Similarly, you write the sum expression. Now you have to simplify this expression. What you can do is first rearrange this. So rearranging this, you get this corresponding for 1, 2, 4, 7. Previously, I have written it for 4, 1, 7, 2. Then you take X bar outside from this expression and X outside from this. You have Y bar Z plus Y Z bar. You have Y bar Z plus Y Z bar. What is this one? This is nothing but your XOR, Y XOR Z, right? And what is this? This is an XNOR gate. XNOR gate is nothing but complement of XOR gate. So we can write XOR complement. So hence this is written as Y XOR Z, the whole complement here. Don't forget this. And then if you consider that Y XOR Z is A, you can write it as you can write it as X bar dot A plus X dot A bar. So what is this can be further written as X XOR capital A, and we know that capital A, we just assume that it is Y XOR Z. So X XOR Y XOR Z. So your sum term here is simply can be written as X XOR Y XOR Z, or this is Z is nothing but your carry in. So it is carry in. Okay. Now similarly coming to the uh, carry term here, C out term. So there are two ways. If you use K-map, then you will have to simplify, and it requires some kind of a thinking to simplify this. The other way is directly from the truth table or directly from the truth table. You can write the corresponding min terms here, X bar, Y, Z, and combine here, pull out Z from these two expressions and pull out XY from these two expressions. You have X bar Y plus XY bar, and XY when you pull out Z plus Z bar. Z plus Z bar is nothing but 1. So here X bar Y is nothing but X XOR Y Z. So this is the expression for C out. Now we have two expressions here. We have two expressions here. One expression was X XOR Y. So if I have X, Y, and Z, three variables, XOR of all these things, XOR of this, and then the XOR of this will be my sum. Okay, I purposefully did 2 gates here. I could have done a 3 gates also, but why I purposefully did 2 gates is because I'm having X XOR Y in my carry out term, so that I can use one of these outputs here. So what is that? X XOR Y is this particular part. I hope you can see. So this is my X XOR and an AND gate of this. Okay, and I've got this particular thing. Now XY AND gate. So XY AND gate, XY AND gate, or of this, because or of this. Or of this. This will be my C out term. Okay. Now this will be your combinational circuit. This will be your combination circuit. Okay, and the same thing can be implemented using the block diagram. The same thing can be implemented using a block diagram. Yeah, this is the same circuit we know, right? And yeah, we have got xy, x XOR y. We have taken AND gate here, and then x dot y is an AND gate, and then OR gate of this we got C out. Now, what is this particular block here? This is nothing but your half adder. This particular part is also your half adder circuit. So which means that you, instead of a gate level design, you can just represent it in a block level design. So you can have two half adders. You can have two half adders. So one output will be x XOR y, and the other output is going to be x dot y. So you can use that, and all you need is, why should we go in for this block diagram? Because sorry, manufacturers, they produce half adder IC separately, full adder IC separately. So if you are having half adder ICs, inside one single IC, you will have multiple half adder blocks. So you can use one single IC to implement it, instead of getting, how many gates are required here? You need an XOR gate IC, you need an AND gate IC, you need an OR gate IC. So these can be simplified when you are using a block level design. Any doubts so far? We will do the subtractor in the next class. Any doubts? Okay. I hope there are no doubts. So thank you. And then don't forget about the instructions that I have given regarding your lab exam. Okay. So thank you so much. Let's meet tomorrow at 2 o'clock.
Excuse me, sir.
Yeah.
Sir, actually, you have checked the doubts that I have put up, and you've written a statement key, you've updated it, but there is still one question that I have doubt in. So do I like respond to that, or?
Yeah, yeah. If there are